So this is what is called the chi-square test. Okay, and what we're doing is over a set of observations, we look at the observed number minus the expected value squared divided by the expected value squared. Okay, and that is what is chi-squared. And then what you do is, now remember, and then you sum over all your observations. You sum over all our observations, and when you look into this chi-square table, you have to associate this probability, okay, the chi-squared value, with the probability associated with the degrees of freedom. Now, what is this notion of a degrees of freedom, and why is the degrees of freedom n minus 1 when the number of things you're observing or looking at, or number of parameters you're testing, is n? Why n minus 1? One simple example is to say let's say I have 4 numbers, and each of those numbers should sum to 10. Okay, now let's say I had no restrictions on what those numbers should be. Should they be negative? Should they be positive? Should they be integers? Should they be square roots, etc.? So what I have to do is, assuming that they're, and to make it simple, we can assume that they're rational numbers, because the point is not the number choices, but this notion of degrees of freedom. And let's say that the rule is that these 4 numbers should add up to 10. Okay, so I can choose any number, negative, positive, integer, natural number, something that has, something that is a fraction. I can choose any of these numbers. Okay, so I choose a number, the first number. I have complete freedom to choose it. I have to choose, let's say I choose 5. Let's say the second number, I have complete freedom to choose that number too. Let's say I choose 2. Just trying to make it simple, just to explain this kind of the notion of degrees of freedom. And a third number, let's say I choose 1. Now, do I have, if my rule states that these 4 numbers have to add up to 10, do I have any choice in my fourth number? I do not, because I have chosen my first 3 numbers and I have the freedom to choose them. And I know that 5 plus 2 plus 1 is 8. And therefore, the last number, in order for me to meet my rules, those specifications, I have to have the 4th number to be equal to 2, which means I do not have the freedom to choose that 4th number. Okay, this is one way to explain it. N minus 1. So then you look at what is called the chi-square table and see the probability associated with the degrees of freedom. And that probability will tell you the probability will tell you whether you should reject the hypothesis, the null hypothesis, that these things that you're looking at are not statistically significant, versus saying that I reject it, I accept it, or I reject it, and I have to go for the alternative hypothesis. Now, this is a really good video, and I would like you guys to take a look at it.
Especially in AP biology, especially in science, is very important. And it's a way to compare, when you collect data, is the variation in your data just due to chance, or is it due to one of the variables that you're actually testing? So the first thing you should figure out is what are said that we had 1 degree of freedom because there's 2 outcomes. 2 minus 1 is 1. So we're in this right here, in this row right here. And then here is our magical 0.05 column. And so our critical value is 3.841. And so if we get a number higher than that, we reject our null hypothesis. We didn't. So we got a value that is lower than that, 0.72. So that means that we have to accept our null hypothesis. That means that my wife did a great job. There's nothing wrong with the coins. We didn't. There's not way more heads than there should be, and so we have to accept the null hypothesis that there's no statistical difference between what we observe and what we expect to see. So now let's try a little more complex problem. Now we've got dice. So we've got 36 dice. So let me get this out here. So our expected values. Well, there are 6 things that you can get. So we can get a 1, a 2, a 3, 4, 5, and a 6. And so let's play this out. So expected values, since I have 36 dice here, we would expect to get 6 of each things that you can get. So we can get a 1, a 2, a 3, 4, 5, and a 6. And so let's play this out. So expected values, since I have 36 dice here, we would expect to get 6 of each of those numbers coming up. So I'm just taking 36 total dice divided by 6, so I get 6. But let's see what we get for observed value. Well, it looks like we're getting a lot of 6s. So if we look at the observed values, for 1 here we get 2 1s. We look at the 2s, we get 4 of those. For the 3s, it looks like we get 1, 2, 3, 4, 5, 6, 7, 8 threes. For the 4s, we get 1, 2, 3, 4, 5, 6, 7, 8, 9. For the 5s, we just get 3. And then for the 6s, look at all the 6s. 1, 2, 3, 4, 5, 6, 7, 8, 10, 2, 2 right here. Okay, now we have to figure out a chi-squared value, so let me get this out of the way. And I'm going to stop talking and do the math and speed up the video a little bit. And so hopefully I don't screw up any of this. So that is 58 over 6, which is 9.6. So that is our chi-squared value is 9.6 in this case, since we added all these up. So now we got to go over here to our chart. And so first of all, we have to figure out how many degrees of freedom do we have. Well, since there are 6 different outcomes, and we take 6 minus 1, so we've got 9. We're in this column of the 0.05 right here. So if I read across, our critical value is 11.07. And so if we look at that, did our value go higher than that? No, it's only 9.6. It's lower than that. So in this case, since it's 9.6, even though we had all of those 6s, we still need to accept our null hypothesis that there is no statistical significance between or difference between what we observe and what.
So this is the chi-squared table, and I hope that video gave you a good idea with some pretty well solved examples. And this is the table, and once again, you want to get 95% probability of your answer being correct, and this is the notion of the degree.